Okay, so in chapter 11, we talked a lot about vectors, and we used vectors with numerical components, and we just kind of dealt with the geometry of vectors, how they look in 3-space, and kind of gaining an importance and gaining a value of the importance of vectors by figuring out, well, I need a vector to define a line, a vector to define a plane, and all kinds of things like that. So this next chapter is on what's called vector-valued functions, and that's where instead of having numerical components for all your function values, you have values that can be created for different points in space, for different times in space. So, how does this look? A vector-valued function maps real numbers to vectors by using parametric equations, which turn into expressions in terms of t, to calculate each component. So in BC Calc, you did a lot with parametrics at the end of the year, and technically you did vectors as well, where you had like a position vector and a velocity vector, and it was all parametric. Same thing here. We're going to use parametric equations as expressions in terms of t to calculate each of our components. So we can have a vector-valued function that's in a plane, and we can have a vector-valued function that's in space, just depending upon the number of terms we have. So if I have 2 terms, I and j only, I would have a plane. If I had 3 terms, this would be in space. Those are vector-valued functions, and you can see that the vector, capital R, is a function of t, where the first component, the I component, is f of t, and the j component is g of t. And then the same thing for R in 3 space, except you have f, g, and h for I, j, and k. And you can write that in component form using the brackets. That's usually where I go. But often you'll see these vector-valued functions looking like this, just so they look a little bit more like a traditional vector. They kind of look, a traditional equation, a function, with each of the components inside. All right, so the domain of a vector-valued function. Domain is always your input. So the domain of a vector-valued function is the t values that are allowed for all 3 components. So basically you find the least restrictive domain that can be input into each of the 3 components. Now your range is your output, so your range of a vector-valued function is kind of an output where you have an x range, you have an y range, I'm using this notation, I made this up, and then you have a z range, where basically your range of a vector-valued function is a range of vectors that each can have their own window. So x might be able to go from negative infinity to infinity, but y only goes from negative 1 to 1, and z is only positive. And it gives you an idea of where this vector-valued function would be mapped in 3 space. So let me kind of explain here. So if I want to find the domain and range of r of t equals sine 3ti, cosine 3tj, and tk, first my domain are the values of t that can be input. Well, sine has values of t of negative infinity to infinity, cosine as well, and t by itself can be anything it wants. So our domain is going to be negative infinity to infinity, and remember, that means t is negative infinity to infinity, not x, okay? Now, if we want the range, we're just going to give the range as a function of 3 separate values. So the sine curve, sine of 3t, sine has a range of negative 1 to 1, so my x window is going to map from negative 1 to 1. Cosine 3t also maps to negative 1 to 1. And t maps to whatever the domain was, which was negative infinity to infinity. So this tells us that if we mapped all the possible values of this vector-valued function, I would get something that goes from negative 1 to 1 on x, negative 1 to 1 on y, and all the way up and down the z-axis. So now if we do domain and range here, root ti, 3t, 4t, my domain really is just restricted by that square root. So my domain is that t is greater than or equal to 0, which you can write in interval notation. And the range, let's see, well, the square root of t is going to be non-negative, so my range there is 0 to infinity. When I plug 0 to infinity in for 3t, I'm going to again get 0 to infinity. And when I plug 0 and infinity into negative 4t, I'm going to get negative infinity to 0 as an output. So again, when you do your ranges are dependent upon your domain. So if your domain is restricted, your range may well be restricted too. And then last but not least, domain and range for this guy. So ln, the input for ln needs to be greater than 0. So 9 minus t squared needs to be greater than 0. And if I think about that graphically, there's 9 minus t squared. It's above the x-axis from negative 3 to 3. So this would be restricted on negative 3 to 3. Those are parentheses, pardon me. This guy right here, 1 minus t, t needs to be less than 1 for that. And e to the t can be anything it wants. So I need to be less than 1 and between negative 3 and 3. So I'm thinking my domain is going to be from negative 3 to positive 1, and positive 1 would be included. So there's my domain. My range now needs to be based on that domain. So if I plug negative 3 to 1 in here, if I put negative 3 into there, it's kind of sort of like ln 0 from the right, which is negative infinity. And if I plug 1 into there, I get ln 8. So then if we look at the 1 minus t here, when I plug in negative 3, I'm going to get the square root of 2. And when I plug in 1, I'm going to get 0. I'm sorry, the square root of 4, which is 2. And then when I plug in 1, I'm going to get 0. So from 0 to 2, 0 is possible. 2 is a parenthesis, because when I plug negative 3 in, I'm not really plugging in negative 3. And then for our z component, I have negative e to the t, plug in negative 3, and I'm going to have negative e to the negative 3. So that's actually going to end up here. So negative e to the negative 3. And when I plug in 1, I'm just going to have negative e, which is technically smaller. So this guy is going to have that as a range. Now, this is obviously super complex. But my point in having this example 3 in here and making it that complex is you have to think about the fact that the domain makes the projections for everything else. So my domain, being negative 3 to 1, is what I plug into here. It's not that I look at the original ranges of each of these functions. I only look at the ranges based on that input. Okay? All right, so now, all this stuff we've talked about, domain and range, that usually has to do with functions, and functions are visual. I can see them. Well, here's what they look like. A plane curve represented by a vector-valued function, such as r of t equals 2 cos t minus 3 sine t, I and j from 0 to 2 pi, is going to look like this ellipse here on the left. Now, how does that happen? Well, it happens like this. Since this only has an I and a j component, that means that it's going to be mapped onto an xy plane. So it contains only the I and j component, which maps it onto an xy plane. Now notice this has an arrow on it to indicate direction. So how does that happen? Well, here's how it happens. You pick values of t. They want values of t from 0 to 2 pi. So here's t, here's x, and here's y. So when t equals 0, I plug 0 into the vector valued function. 2 cos 0 is 2, and negative 3 sine 0 is 0. So I plot the point 2, 0, which is right here, and technically it's a vector. It's the vector 2, 0, but basically, historically, what we've read this to mean is if it's a vector-valued function, yes, there's technically an arrow there, but we only care about the end point of that vector when sketching a space curve. So it goes to that point. Now, let's say when t equals pi over 2, 2 cosine pi over 2 is 0, negative 3 sine pi over 2 is negative 3. Now I'm down here, which is why this arrow points in that direction. Because when you have a vector-valued function and you graph it on a plane or in space, it has direction. As t increases, that thing maps itself out in a certain order, and the arrow indicates that order. Now, does it matter what order? Sometimes it depends on the context. All right? So what about more plane curves? A plane curve can often be written in both component and or parametric form. So if I have a picture of this and it's on an XY plane, can I write it in rectangular form? Rectangular form means XY form. So let's say I have this vector valued function. I have x equals 2 cos t, y equals negative 3 sine t. This is component form or vector form. This is parametric form. And then you can also get it in rectangular form when you just eliminate the t completely. Now, one way to eliminate t completely would be to solve for t and then substitute, but I've got a better idea. Instead of solving for t and substituting, I'm going to use a nice little trick that says, you know what? I know that sine squared t plus cosine squared t equals 1. Fine. How is that helpful? Well, sine of t is y over negative 3. Therefore, sine squared of t is y over negative 3 squared. And cosine squared t, x over 2 is cosine. So I can put that there, and this is like a creative substitution technique. One of the things I didn't realize about mathematics until I got to college is that when I look at something, I can never tell if there's going to be a substitution that takes place, and as you get into upper level mathematics, you'll start realizing that substitution is a huge component of mathematics. At first you learn substitution as like a freshman or younger, and you do those problems with the cereal, and you're like, if I have 2 boxes of Trix and 3 boxes of Cocoa Puffs and it costs me $9.75, and then I buy 1 box of Kix and 5 boxes of Cocoa Puffs and it costs me $12.50, how much does each type of cereal cost? And you've got that system. If we said, oh, you can do elimination or substitution, yeah, that's all fine and good, but substitution is incredibly useful. And it's the idea that if you have one thing that equals another thing, you can swap those guys in and out at your leisure as long as your domains and whatnot hold true. And that's what we're doing right here. So this parametric equation turns into this rectangular form, which is going to be y squared over 9 plus x squared over 4 equals 1. And if you're familiar with conic sections, you know that's an ellipse centered at the origin with a minor axis of 2 and a major axis of 9. Not 9, geez, 3. So there's my minor axis of 2, there's my major axis of 3, and there's my ellipse. All right, and then we have space curves here. So that's in a plane. Now when we have in space, when you have a cosine and a sine and a z component as well, you get a helix, and that's just pretty cool. So long story short, if you want to define a string moving through space, a nice curvy line that's just meandering its way through space, however it goes, the only way to define that is with a vector valued function or a set of 3 parametric equations. A line in space had 3 parametric equations, and if you want to make it curvy, those parametric equations are non-linear. In a line, we had like 2t plus 4, 3t minus 7, and t plus 2. When you start dealing with curves, I have x equals 4 cosine t, y equals 4 sine t, and z equals t. I can make those t's squared. I can throw ln's in them, whatever I want. It'll make it turn from a straight line into a nice curvy shape. Okay? Enough rambling. R of t, blah, 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 contains I, j, and k components, and it is mapped onto an x, y, z field, a space field. So if I want to plot points here, when t equals pi over 2, r of pi over 2 is 4 cos pi over 2, which is 0. 4 sine pi over 2 is 4, and t equals pi over 2 would be pi over 2. So the point 0, 4 pi over 2 is this guy right there. And then when t equals pi, r of pi is 4 cos pi, which is going to be negative 4, 4 sine pi, which is 0, and t equals pi is pi. So negative 4, 0 pi is this guy. Nope, not that guy. So negative 4, 0 pi is this guy over here in the back. And then an arrow would go in that direction because as t increased, that's where it went. So that's how you draw a helix. Pretty cool, right? All right, now we're supposed to sketch this guy. I will not make you sketch a lot of things, but it's important to think about how something would be sketched. So if I go from 0 to pi over 2, I'm going to have r of t, and I'm going to have t, and I'm going to make a table. So I'm going to go 0, I'm going to do pi over 6, I'm going to do pi over 3, and I'm going to do pi over 2, just for yucks. So at 0, I have sine 0, cos 0, 0, which is going to be 0, 1, 0. And pi over 6 is like 30 degrees, so that's going to be 1/2 root 3 over 2, pi over 6. Pi over 3 is like 60 degrees, so root 3 over 2, 1/2, and pi over 3. And at pi over 2, I'd have 1, 0, pi over 2. So how do I plot this? Well, here's how. I make my x, y, and z axes. And then I start plotting points. So 0, 1, 0 is right about here. We'll call that 1. And then 1/2, 3/2 pi over 6 means I'm going into the positive x. Y has decreased a little bit, but I've got to go up a little bit. So I don't know. It would kind of sort of be plotted right there, which I know is a little bit weird. But we are technically going up because this would be like 1/2. So if this is 1, this would be about 1/2, and this would be a little bit less than that. And then I have to shift up on the z-axis. And then at pi over 3, I go down a little bit more on the y, but up a little bit more on the x. So it's like here. But then I have to shift up more on z, and then 1, 0 pi over 2, maybe like that. Now, I am terrible at drawing these things, but basically, I'd have something that curves like this. Again, mine is not perfect at all. But that would be a section of that vector value function. All right, so I'm at quite a few minutes here. I'm going to stop this video here so that you can take a break. There is one more video to get us through this last page because there's a lot on it. Pardon me, the last 2 pages technically. So take a breather and then come back. Our joke of the day is a Christmassy joke. What do elves study in school? The alphabet.